All right, let's dive right in. Today, we're going to pull back the curtain on what is, no exaggeration, the single most important invention in all of modern electronics. CMOS technology. It is the invisible, unsung hero powering the screen you're looking at right now, your phone, your car, pretty much our entire digital lives.
And to get our heads around it, let's start with a question you've probably experienced but maybe never really thought about. Why does your laptop get blazing hot when you're gaming or editing video, but then when you just close the lid, it can sip power for hours, even days? How is that even possible? Well, the answer is hidden in the beautiful, elegant design of billions of tiny little switches.
Okay, so let's get to the core of it. To really understand digital circuits, you kind of have to do a mental reset. Forget everything you might have heard about transistors being these little amplifiers that just make signals bigger. For the digital world, we need to think about them as something way more fundamental, and actually a lot simpler.
And that simpler way of thinking is this. Is the switch on or is it off? That's it. 1 or 0, high or low. Our entire complex digital universe is built on that one simple binary question. The goal isn't to amplify anything, it's to create the most perfect, most efficient on-off switch imaginable. So to do this, we have two main flavors of these switches, and they're perfect opposites. First, you've got the NMOS transistor. Think of this as your pull-down switch. Give it a high signal, a 1, and bam! It connects the output wire straight down to the floor, to ground. Then you have its counterpart, the PMOS transistor, which is the pull-up switch. It does the exact opposite. You give it a low signal, a 0, and it connects the output up to the ceiling, to the power supply.
And this is where the magic happens. The C in CMOS stands for complementary. We pair these two opposite switches together. So for any given input, one switch is guaranteed to be on, while the other is guaranteed to be off. They're never on at the same time. And that brilliant little trick prevents a direct short circuit from power to ground. That is the secret sauce to its incredible, world-changing power efficiency.
So now we have our fundamental building blocks, right? Our little logic Legos, the pull-up and the pull-down. Now the fun starts. Let's see how we can start snapping these together to build things that can actually, think.
The most basic thing we can build is the inverter. It's about as simple as it gets, just one of our PMOS pull-up switches stacked right on top of an NMOS pull-down switch. If you send in a 1, the bottom NMOS switch turns on and yanks the output down to 0. If you send in a 0, the top PMOS switch turns on and pulls the output up to 1. It just flips the input. Simple, elegant, and it's the atom that all other digital logic is built from.
So how do we build something a little more useful, like a NAND gate? Well, it's just a clever recipe. Let's think. We only want the output to be pulled low when input A and input B are both high. So we put two of our NMOS pull-down switches in a series, like a chain. Both have to be on to connect to ground. Now for the pull-up part, we do the logical opposite. We put two PMOS switches in parallel, side by side, so the output gets pulled high if either A or B is low. Slap those two networks together, and you've got yourself a NAND gate, a truly fundamental piece of computation. Now, in a perfect world, all our signals would be clean, crisp 1s and 0s. But we don't live in a perfect world. The real world is electrically messy. There's interference, there's noise, signals get fuzzy, so our circuits have to be tough enough to handle that reality without getting confused. This is where a concept called noise margins becomes absolutely critical. You can think of them as safety buffers. A logic gate doesn't need to see exactly 0 volts to call something a 0. It might say, hey, anything between 0 and, say, 1 volt, I'm going to count that as a 0. That 1 volt buffer is its noise margin. It's the amount of electrical garbage a signal can have before the gate might make a mistake.
So naturally, the goal of any good circuit designer is to make those safety zones, those noise margins, as wide as they possibly can. That's what ensures a chip is robust and reliable, making the right decision every single time, even when the signals coming in aren't perfectly clean. Okay, so our circuits are robust. They're reliable. Now let's talk about speed. What is the one fundamental physical barrier that dictates how fast a processor can possibly run? What's the ultimate speed limit?
Well, the answer is a little thing called capacitance. The best analogy is to think of every single wire and every transistor input as a tiny electrical bucket. To signal a 1, a PMOS switch has to literally pour electrical charge into that bucket to fill it up. To signal a 0, an NMOS switch has to open a drain and empty it all out.
And here's the catch. Filling and emptying that bucket isn't instantaneous. It takes a tiny, tiny amount of time.
That little slice of time is called the propagation delay. Now, multiply that tiny delay by the billions of switches flipping every single second inside your processor, and that right there is the physical speed limit of your computer's clock speed.
So we're starting to see this trade-off, this constant battle between being reliable and being fast. But there's a third, massive factor in this whole equation: power. And wherever you have power consumption, you have heat. Which brings us right back to our very first question: why does your laptop get hot?
When we talk about power in a chip, it really comes in two flavors. First, there's static power. That's the energy the chip leaks when it's just sitting there, doing nothing. And thanks to that amazing complementary design of CMOS, this is practically zero. It's incredible. But then, there's dynamic power. This is the energy you burn every single time you fill and empty one of those buckets. Every single switch from 0 to 1 and back again burns energy, and that is what generates heat.
This leads us to what is probably the single most important equation in modern chip design. Dynamic power is equal to F, the frequency or switching, times C, the capacitance or size of those buckets, times VDD squared, that's the supply voltage, squared. This is the fundamental recipe for power and heat.
So this simple little formula gives engineers three main knobs to turn to make chips more efficient. They can try to design them to switch less often, which lowers F. They can keep shrinking transistors to make the bucket smaller, which lowers C. But the biggest lever, by far, the magic bullet, is voltage. Because it's squared in the equation, even a tiny drop in voltage gives you a huge reduction in power and heat. Whew, okay. We've gone from a simple on-off switch all the way to the deep physics of why your laptop burns your lap. So let's just take a moment and boil this all down to the absolute must-know takeaways.
First, that complementary pairing of NMOS and PMOS switches is the whole reason our devices are so incredibly power efficient when they're idle. Second, speed isn't just a number, it's a physical limit set by the time it takes to charge and discharge all those tiny electrical buckets. And third, almost all the power and heat is generated during that switching, and voltage is the king when it comes to controlling it. The entire art of modern chip design is just a constant, delicate dance between these forces: speed, power, and size.
You know, it's just wild to think that this one simple idea, the CMOS switch, has been the engine of progress for half a century. But we are pushing up against the hard limits of physics. And it makes you wonder, what comes next? What's the next new kind of switch that's going to power the next 50 years of innovation?
Hey, if this explainer helped you see the invisible magic inside our digital world a little more clearly, the absolute best way to support us is to hit that subscribe button, give this a like, and ring that notification bell so you don't miss our next deep dive. Thanks so much for watching.